Okay. Now let us look at now the lecture number 3. Yes, this is the MOS physics. Okay. So what we have seen in the last class, we have stopped the PN junction diode, right? Okay. So what is the basic about the PN junction diode? What we have learned? That means when a P-type semiconductor and N-type semiconductor connect near to each other or maybe connect each other, then definitely the junction will be formed. Okay. Near the junction, depletion region will be formed, or that is called a space charge region will be formed. Okay. If you want to see the current in that particular diode, okay, the potential that we must apply should be more than that of built-in potential of that PN junction. Okay. If you're not able to provide the potential difference between the P and N side, definitely we are not able to send the current. So based on that one, we can say the PN junction diode is actually reverse biased or maybe forward biased. Okay, that's what we have seen. Okay, let me recall in this way also. So if you take, this is what a simple PN junction diode. Okay. Okay. So at the middle, you can see there is a junction is formed something like this. Okay. Consider this is a P-type. This is a N-type. Okay. So what we can observe here, there are holes, plenty of holes will be there. Am I right or not? And you can see these are the different atoms. Okay. And this is the electron side. Okay. So what is happening here? Near the junction, the holes and electrons are recombined each other. Therefore, these two holes and these two things are combined each other. That's the reason why there is a space charge region or immobile charge will be available near the junction. So that means this is the portion where we can see, this is the portion where we can see the junction is near the junction. We can see this one, right? Till this point, you can see there is no free carriers. As you can see, observe carefully, there is no free carriers are available because these two free carriers are combined each other. Therefore, this is the place that we can observe at the middle. Okay, as you can see, there is no carriers here. There is no carriers for this particular ion, right? The moment if the free carrier is not available, the atom becomes ion. Okay, on the left hand side, it is a negative ion. The right hand side, it is a positive ion. Okay, so therefore, definitely there is some built-in potential is existed here. This built-in potential we can call it as VB, for example, built-in potential. What is the built-in potential formula? Anybody, any idea? built-in potential. Okay, so that's what you have learned from the EDC subject, right? Okay, neta VT ln Na into Na ND divided by Ni square. Okay, that is what the built-in potential. Of course, this is not the course for us to establish that kind of equation, but we should know what is the equation that counts the built-in potential, right? Good. Now the question is, in our analog electronics, what we are going to do is that how we are using this diode in our circuit design. Okay, that means you should know a little bit fundamental related to this one, right? Okay. Now, as I mentioned that if the carriers are moving from N side to the P side, for example, if the carriers would like to move from N side to the P side, then the current is also in the same direction. Okay. So then if the current is moving from one direction to another direction, definitely we can call it as it is a forward bias. If the current is blocked, for example, it's not going, okay, then it is say that it is a reverse bias. The question is when it is a forward bias, when it will become reverse biased. Okay. Yes. Look at this one. So what is the symbolic representation of this one? Okay. This is what the symbolic representation of a diode, right? So this is the N side, this is the P side, and this is the N side, right? Okay, so we need to know that we should say that if this is, if it has more strength than this side, okay, then it is, okay, less strength. Then we can say that the diode is in forward bias. Okay, so that means that it just like act as a, just like a short circuit from one end to another end. Current will flow from P side to the N side. For example, if the P side is less strength compared to the right side, then what we should say? P and N. Okay. More strength and less strength, which implies forward bias. If it is less strength and more strength is here, then we can say reverse bias. Am I right? Okay. Now let us take simple examples. Okay, by applying some real potential to the N side and P side, we should say which one it is in here. Okay, let us say, for example, this is 5 volts that we are applying at the P side, for example. Here 2 volts that we apply at the right side. That means P side is actually 5 volts, N side is at 2 volts. So which side is more strength, having more strength? P side is actually, you can see, more strength compared to the N side. That's the reason why it is in reverse bias. Sorry, it is in forward bias, right? Are you agree with me? Okay, right. For example, this is minus 2 volts. This is minus 5 volts, for example. And can you say what it is? It is in forward bias, right? Because the minus 2 is higher than that of minus 5. That's the reason why it is in forward bias. Now, for example, minus 2 plus 20. Of course, we should not apply that much. Definitely. Let us, for the argument's sake, we are applying 20 volts. What it will be there? It is in reverse bias because N side is stronger than that of P side. For example, something like this. 2 volts and 5 volts. And what we can say? It is also reverse bias. Okay. So the question is, so whether we are applying the positive potential or negative potential is not a matter. The P side always should be, the strength must be more than that of N side. Then we can say it is a forward bias. Otherwise, it is in reverse bias. Excuse me. Right. Let us take, this is the one way of looking at whether the PN junction is actually a forward bias or reverse bias. Another way is also there, as I mentioned previously also, just take the potential difference, okay? So the potential difference between P and N, okay, it is called VPN, for example. The P side to the N side. It is also called as potential at the P side minus potential at the N side. Take the difference. This value always should be greater than 0. What does it mean? It always positive. It always positive. It should not be negative or 0 also. As I mentioned that, for example, if you take 0 volts here and 0 volts here also, what we should say? It is also reverse bias. See, what exactly meaning of the forward, making the forward bias? The diode, what do you mean by saying that the diode is a forward bias? Forward bias means that, you see, we are applying, we are putting some potential here, okay? Make the holes to move towards the N side. Am I right? That means we are making the holes to jump the space charge region. If you're able to make the carriers jump from the jumps to the built-in potential or maybe the junction, then definitely we can call it as a forward bias. Okay. For example, if it is very less strength, for example, if you're applying the positive potential here, that means more potential. More potential in the sense in this case is a positive potential. For the positive potential, holes will be repelled and it will go towards the N side. Okay. For example, if it is negative, for example, okay, if it is negative, what do you mean by negative? That means it is less compared to that side. Okay, in terms of positive and negative, we should say that whether high potential we are applying, low potential that we are applying. That is the very best suitable way to, we can say, not that a minus or plus. Okay. Okay. So therefore, if the plus is means that the holes will be moved towards the N side. The minus, if you write here, for example, if you take the less potential, for example, then holes will be attract towards this left hand side. Then definitely what will happen? The space charge region will increase. That means the carriers are not jumping. If the carriers are not jumping through the junction, then definitely we should say that there is no current will flow. Therefore, it is definitely we can call it as a reverse bias. Okay. So based on whether the carriers are crossing the junction or not, you should say whether the PN junction diode is forward bias or reverse bias. Right? Okay. So therefore it is self-explanatory that more or less the words that you can understand very clearly now. Okay. One more thing is that, for example, if you take, this is also the potential difference between the P side and N side also. For example, if it is for the first case, if we consider, therefore it is a 5 volts that I'm writing here, and this is 2 volts, this value becomes +3. Therefore, since it is a positive, the diode is in forward bias. Okay. For example, this is a -2 minus of -5. Therefore, definitely it is +3. But in this case, -2 minus of +20. What will happen? -22. It is in reverse bias. Okay. So for the third last case, for example, -2. Sorry, I think what is this one? 0 and 0, for example. 0 volts minus of 0 volts, it becomes 0. Therefore, since it is a negative, since it is 0, and since this is positive, since it is positive, therefore these two are forward bias, these two are reverse bias. Okay. For example, if I say that we would like to make the PN junction diode is reverse bias, then what you should say? If I ask you that you want, I want to make the PN junction diode is reverse bias. What is your suggestion to me? N side should be more reverse bias. If you want to make the PN junction diode is a reverse bias, then what suggestion that you have to give on P side and on N side? P side should be more or less. It should be less. Okay. P side should be very, very less compared to the N side. Then it becomes reverse bias. Are you getting the point? If you ask you to the forward bias, then what you should say? P side must be more strength than that of N side. Please remember this word. Okay, right. So this much information is sufficient about the PN junction diode when we are talking about the analog circuits. Okay, right. Now let us look at the physical structure of MOSFET. Okay, the physical structure of MOSFET. Okay, so why we use the why we need to talk about the MOSFETs? Why we need to talk about the MOSFETs? As you know that all the analog electronic circuits are nowadays are realized by using the MOSFETs only. Okay, because of various reasons. One of this one is very less in cost. Okay, in a given area, more number of transistors can be accommodated, and it occupies it consumes less power as well when compared to the bipolar junction transistors. Okay, so in the analog circuit point of view, it is mainly used for amplification. Okay, so therefore, definitely we need to talk about a little bit physics on the MOSFET. Okay, so what is the MOSFET? Well, MOSFET is a 3-terminal device or 4-terminal device? Huh? 3-terminal device. Okay, fine. Okay, let us take this is the one. Okay, so if you want to realize the nMOS transistor, okay, as you know, what are the 3 terminals? Can you please let me know what are the 3 terminals? The source. Have you heard about the gate? Have you heard about the source? Have you heard about the drain? Okay, there is actually MOSFET is a 4-terminal device. The body is also will be there, right? It is a 4-terminal device. MOSFET is. And one more thing is that if you want to realize nMOS transistor, what should be the body? What should be the body? Body should be P-type body, right? It's a P-type body. So P-type semiconductor I have to take for the nMOS transistor. Okay. On top of it, what we have to do, we have to realize the gate oxide. We have to realize gate oxide, right? Okay. On top of it, we have to realize polysilicon or a metal gate. Metal gate, right? And we have to realize source and we have to realize source and drain. Therefore, this is called one material called N plus material. This is also N plus material. This is the P type. So as you can see that here you can see one terminal. It is called one terminal. This is the second terminal. This is the third terminal. And definitely we have here another one is called P plus. This is a body actually. We take this body as well. Okay. Of course, keeping the terminal at the ground is not the suitable way. Just we have to keep it just adjacent to the 10 plus material only. But for the sake of explanation, I have given there in that position. Right. Okay. So the MOSFET is actually a 4-terminal device. Okay. And let us see what is the purpose of using the body. The purpose of the body, this is called body. This is called body or substrate. This is also called body or a substrate. What is the purpose that we have to use a p-type substrate or a body? This is actually used to give the mechanical strength for the active areas. So these are called active areas, right? This is one active area. This is another active area. N plus active area. This is another active area. Okay. So in order to give the strength to a particular active area, we have to create bulk or a body. This is also called as a bulk also. This is also called as bulk. Okay. So only for the giving the mechanical strength, but it should not provide any kind of conduction between any other materials. As you can see, this is a p-type material. This is n-type material, right? This entire thing is actually a p-type material. On top of, within the p-type material, I have realized the n plus and n plus, right? That means whenever n and p are near to each other, definitely what will form? P-n junction will be formed, right? Okay, so therefore here, near the junction, that means here, what will form? P-n junction between n plus and this is p. So between the n plus and p, there is a possibility of p-n junction. Okay, something like this. This is n plus, this is p. Okay, definitely say, forget about what is the doping concentration at this moment of time. Just like a p-n junction diode. This side as well as this side you can observe, right? In the both sides that there is a possibility of p-n junction will form. Okay, so if it is a forward bias, what will happen? The current will flow from the n plus material to the p side. Okay, active material to the bulk, the current will flow. That is not acceptable. Okay, that means we have to make that is a reverse bias. Can you tell me what potential I shall have to apply on a p side, what potential I can apply on n side so that it will always reverse bias? That means as you can see that this is a, this should be what this one, reverse bias. Reverse bias means very, very less. Okay, very, very less compared to this side. It should be more. Are you agree with me? Okay, that means so we have to make this value is equal to very less compared to the whatever the potential that we apply at n plus station. Okay, therefore, so if you take this something like this, okay, VPN. Okay, so VP minus of VN. Let us consider in this way. Okay, what is the VN should be so that it always in the reverse bias? What is the one value that makes it always in the reverse bias? Whatever you keep it here, it doesn't matter, but what should be? That's what I'm keep on asking you to, you have to pay attention, right? Okay, so if you understand about this particular concept, then you're able to you're able to tell me what is the right answer for that. Minus. If it is minus, for example, okay, if it is minus, for example, minus value, if it is a positive, what will happen? There is a possibility of more negative will be there, right? So one possibility you can consider is, yes, it is absolutely, it's a negative. If it is a negative, what will happen? If it is a negative, this is also negative. Total, it will be negative. Fine. So reasonable way of taking this value is 0, for example. 0. It is 0. So if it is 1, for example, if it is 0, or it is 1, it is 2, it is 3, whatever the value you put it here, the VPN value is always negative. Am I right or not? VPN is always negative. 0 minus 1, 0 minus 0, reverse bias. 0 minus 1, 0 minus 2, 0 minus 3, something like this. We have to keep it like this. Okay, that means this value is always connected to what? 0. Therefore, we make sure that there is no forward bias junction between the active area n plus to the substrate. Okay, so we never ever flow the current from active material to the substrate. Are you agree with me? Yes, this is what we can say. Okay, therefore this is called actually n-type n-type MOSFET. Okay, n-type MOSFET. Okay, let us understand more detail. Don't worry. So this is the simple structure of a nMOS transistor. Let me rewrite this one again. Okay, redraw this one. Okay, copy and then paste here. Okay, better I can consider this is in this way. Okay, so instead of following this, so if it is 0 means that definitely it is connected to ground. Okay, 0 or ground is one and the same. Okay, so electrically we can say that there is a 0 potential means that it is connected to ground. Okay, G and D. Okay, why we have connected the body of the nMOS is connected to ground? Why we have connected the body of the nMOS is connected to ground? In order to avoid the current flow within the body. Okay, because these materials can form all the n plus materials can form the junction with the each substrate. That's the reason why we don't allow any kind of current flowing inside of the body. Okay, the current must flow in a specific region. That region we are going to talk now. Okay, fine. Now, let us assume that, let us apply some positive potential we applied on this particular place. Let us apply a positive potential is applied on this place. What will happen then? So as you can see that the top is actually a conductor material, and below that one there is an oxide. This is called an oxide. This is SiO2 actually. It is an insulating material. Insulating material. This is a conductor. Of course, below this one, it is also it is actually a semiconductor. Okay. Definitely, two conducting plates are separated by silicon dioxide, right? Then what we can call this is, what component we can call this is, if the two conducting plates are separated by an oxide or insulating material, what we can call it as capacitor. Simply, it is a capacitor. So this capacitor is called MOS capacitor, right? Okay. So this is what actually we can see. So this is what we observe. So this is one conducting plate, okay, and this is another conducting plate, and separated by, this is a one conducting plate, this is another conducting plate. It is a MOS capacitor. Why it is called a MOS capacitor? So the top plate is a metal, middle one is an oxide, bottom one is a semiconductor. Okay, this capacitor is formed with metal, oxide, and semiconductor. That's why it is called a MOS capacitor. Okay, so what happens if you put a positive charge on top of the plate? Can anyone help me? What will happen if you apply a positive charge on top of the plate? From the capacitor action, we should say that equally and opposite charge will be induced on the other plate. A negative charge will be induced on the other plate. Why? Because an electric field is existed, and because of that electric field, a negative charge will be developed. Okay, so therefore, in this particular situation, what will happen here? In this particular situation, what will happen? Because of this positive charge, actually, what is having here in this particular p-type? As we know that p-type means something like this, holes, right? Am I right? Acceptor atoms will be there inside of it, right? So because of this one, here ions will be absorbed here. Why ions will be available here? Can anyone help me? Because of the positive charge, all the holes are repelled from the bulk, and it will left with immobile ions, negative ions. Therefore, this positive charge and this negative charge will be terminated. This, whatever the positive charge at the top, will be terminated on the other side, negative charge. Okay, therefore the electric field is perfectly balanced. Am I right? Okay, now if you apply more positive, let us apply more positive. We put a more positive on top of it. What will happen? Again, this is old school that negative charge here, negative charge here, negative charge here, negative charge. Because how much positive charge you put it on the plate, the equally opposite charge will be induced on the other plate. Agreed? So this phenomena is called depletion mode. What we can call this is depletion of carriers. That means the region where, look at this one, the region where under the silicon dioxide, the free carriers are depleted from this one. The free carriers are depleted from this one, left with the immobile negative charge. So this is called depletion region. Agree? Okay. Now let us apply more positive on this one. Let us apply more positive on top of the plate. Okay. As you can observe, the moment if I'm applying the positive charge on the top plate, the region of oxide, that means the distance between the plates will be increases, right? See, what is an oxide actually? What is an oxide? It is also consisting of immobile ions will be there in it. దాంట్లో కూడా ఏముంటాయి? Immobile ions will be there in it. Okay, now we are adding some more immobile ions below the oxide. That means all together. So from this point to this point, can we say this is the oxide thickness? Initially, what is the oxide thickness? This is the oxide thickness. Am I right? Tox. This is the oxide thickness. Now, because of the positive potential you applied below that oxide layer, you can see the depletion, the oxide thickness will increases. What happens to the capacitance if the oxide thickness will increases? Or insulated, the distance between the two plates are increases, what will happen to the capacitor? storage will increase. Carefully think about it and tell me. In the last session also we have seen, if the distance between the two plates are increases, what will happen? What is the capacitance? C is equal to epsilon A divided by D, where D is the distance between the two plates, A is the area of the plate, and epsilon is the permittivity of the medium. If the distance is increases, what will happen? The capacitance value will decrease. If the capacitance values decreases, okay, we are not able to provide the more electric field to repel the carriers. It is not possible to repel the carriers, okay, and more electric field cannot be existed there. Therefore, less electric field is available. Therefore, further depletion of the carriers is not possible. Are you getting the point? Further depletion of the carriers is not possible. Okay, therefore, certain limit is there up to that point. Therefore, whatever the potential you put it on the top of the plate, that cannot give you the equivalent opposite charge carriers below the silicon dioxide. Okay, but in fact, what will happen, you know? So these electrons, you can look at carefully. These electrons, whatever the n plus region is, you know, these have plenty of electrons will be there in it. Okay, how much that you put it here? For example, let us consider another positive charge, you put it there, but that much amount of the negative carriers cannot be developed below of that one. Instead, the negative charge will be developed because of the free carriers that are available in the n plus region and that will occupy below the silicon dioxide. That is also a negative, electrically negative charge, electrons. Are you getting the point? Therefore, how much positive charge you put it on the top plate, the equal and opposite charge will be available below the silicon dioxide. Okay, therefore, the electric field will be balanced there. Okay, so therefore, these carriers will be available more and more while we are applying the more positive charge on the top. Okay, these carriers, okay, whatever the carriers you see here, these are actually free carriers. Below is actually immobile ions. On top of it, what are the free carriers? Those free carriers are called inversion charge. What we can call it as inversion charge. Very, very important. It is an inversion charge. Free carriers below the oxide are called inversion charge. Are you getting this point? How a free carriers are available below the silicon dioxide? Everyone is clear? Okay. So this free carriers or inversion charge is called a channel. This inversion charge we can call it as channel. This is also called as a channel. Okay. So this inversion charge, we can call it as a channel. So yeah, these free carriers are because of the n plus region. Okay, so the moment if you write here, n plus here, this particular n plus region have plenty of electrons, right? Heavily doped n plus region, n plus. That means it have got more and more number of free carriers are available in it. That two electrons. Okay, so therefore, the moment if you put a positive charge on top of it, okay, so these free carriers will accumulate or available, occupy this particular portion. Okay, of course, this is also side n plus. Okay, so because some of this and all together, it will be scattered uniformly under the silicon dioxide. Okay, so therefore these free carriers will increase more and more. Okay, when we increase the more and more positive potential, apply the more and more positive potential. Okay, therefore, since it is the number of free carriers that is available under the silicon dioxide, this particular region we can call it as inversion region. This is called inversion region, or inversion charge also we can call it as. Okay, technically speaking, it is called channel. Okay, what type of channel this is? What type of channel this is? N channel. Okay, it is N channel because here we are the channel consisting of electrons, right? Since it is an electrons, it is called N channel. Okay, the plenty of carriers that are available. Okay, this is the second point everyone should know. Okay, what is the first point that we should know? The body of nMOS transistor always connected to the ground. That's the first point in order to avoid the current flow within the body. The second point is that how the inversion charge will be developed or how the channel will be formed. Okay, so you may observe that see, this inversion charge is not because of only few positive charge on top of it, right? Certain potential I have applied. Okay, so at that particular potential only the carriers will be developed. Otherwise, the carriers cannot be induced. The free carriers cannot be induced. Am I right? So therefore, that is the reason why a certain voltage is required. That voltage will give you the inversion charge. So that voltage we people will call it as threshold voltage. Okay, the threshold voltage. Okay, let me write here. Threshold voltage. The minimum, it is the minimum voltage we apply at the top plate to produce inversion charge. Inversion charge. Actually, you know, the body is actually plenty of electron holes actually. Actually, what body has got? Plenty of holes. But what, because of this potential we applied, the surface of the body near the oxide make them convert into N type. And throughout the body is a P type actually, but under the silicon dioxide, it completely converted into a N type. It's completely converted into N type. Okay, so that's the reason why it is called N channel MOSFET. So we cannot call just like that inversion is, we should not say just like that. Okay, because how many, whatever, since it is a P-type some material, but now some part of the P-type material is converted into N-type material. Okay, at what voltage, technically speaking, the P-type carriers are equal to the N-type carriers. So then only we can say that it's an inversion. Okay, so this is what we should know about the inversion chart and channel. Okay, we stop here today, and tomorrow we are going to see the remaining two terminals. Let us apply the potential difference between the two terminals. Because the free carriers are available, it's just like a conductive material. We make them as a conductive material. Apply the potential difference. What will happen? What are the things that you should know? We will see. Okay. By the way, I want to give the two names here before leaving. Just let me give you the name of this one. This is the body. This is the gate. Okay. This is called gate. And what about the other two terminals? We will see in the next class. Okay. One terminal of the body is, one terminal of the MOSFET is body. Another terminal that we have seen so far is gate. This is called a gate and body. Okay, we stop here today and we will see in the next class.